वैसे मेरा आवाज बहुत बड़ा है. My wife always keeps scolding me for that. So the handwriting is okay, no? Visible? Now while writing, it may happen that it goes smaller, the font size becomes smaller. When Burgen. Huh. Yeah, this is Glibichuk. Koniagin. Yeah, yeah. वो मैं शायद तो पहले ही खत्म कर दूं. हाँ, हाँ.
So, good morning everyone. And maybe I should say that other than me, there were 4 organizers for this working. One is Messenger, he is a postdoc here. One is me, I can see it. Second is Dave Woman. One is Gaurav and one is Pastor.
Okay.
So, we are ready. Messenger is sharing. Each of them will be sharing one.
So what's the name? Sorry. Papi. Okay.
Papia.
Papia. It's not by any chance a name of named after a bird, right? Papiya. Yeah, हिंदी में पपिया बोलते हैं, बंगाली में पापिया.
So, we welcome the second day of the group meeting, and it's my great pleasure to welcome Professor Gyan Tokan from HRI, and he is going to talk about an exposition of Urgin
Glibichuk, Koniagin, explanations. Thanks, Mrityunjay. Don't worry, I can't pronounce most of these names anyway myself, as Suri keeps on pulling my leg. He will not let us work. So, huh? What? Oh, forget it. All right. So, okay. So, you see, I will state the result uh, and give you one motivation of doing it. To give an application of it. But more than the application, actually, what is interesting to note is that there is a notion of approximate groups. We all know what is a group is, but many of you may not know what is an approximate group. We all know what is a ring, but you may or subring, but we may not know what is. Many of you may not know what is an approximate subring. Okay, so in this talk, what I will do is that I will state the result and give you an aerial view of the proof of the theorem. When I say the aerial view, that means that I am oversimplifying the proof, and the reality is tougher than what I will be presenting, and so the details of the proof will involve a certain number of things. So it will involve Bellux-Zemery-Gavas theorem, and Bellux-Zemery-Gavas theorem in its own will not be sufficient. There will be an asymmetric Bellux-Zemery-Gavas theorem, and then there will be a Feynman sum product theorem. These are the two main ingredients involved in the proof. None of this involves anything fancy. None of this, neither the statement nor their proof involves anything fancy. It's just a clever use of averaging argument repeatedly. Okay? But as I was telling Suri that these things are nevertheless a work of many great mathematicians. And so in case any of you are interested, we can discuss. I can go into the sum of the ingredients. I can go into the details later on. Or depending on your enthusiasm and your energy, we can go to from aerial view to microscopic view. Okay? But in this talk, we will be restricting ourselves to aerial view. All right. So what is the statement? So the statement is following. So let me abbreviate by this BGK. Okay? The statement of BGK theorem. What does it say? It says that given epsilon greater than 0, there exists delta is equal to delta epsilon greater than 0. So when I write this delta is equal to delta epsilon, which means that it will depend upon the epsilon and it will not depend upon any other parameter which I will introduce later on. As since we are all are in number theory and many of you are in analytic number theory, it is absolutely vital that our parameters depends on which other parameters and does not depend upon which other parameters. Okay, fine. I'll try. And P0 delta, a natural number, such that the following holds. So what are the assumptions? So the assumptions are following, that P is a prime, P greater than P0 delta, epsilon here. Okay. P is a prime greater than this natural number, so it is sufficiently large depending upon epsilon. Okay. So that is one assumption. 2, H subset of Z mod Pz star is a multiplicative group. All right. So it's a multiplicative group. 3, cardinality of H is greater than P to the power epsilon. All right. So these are the 3 assumptions. That P is a prime which is sufficiently large depending on epsilon. H is a multiplicative subgroup of Z mod Pz star, and cardinality of H is greater than or equal to P to the power epsilon. Then the conclusion is that summation H belongs to H. EP H xi 1 by P. Okay. This modulus is, so everybody understands this notation. Is there anyone who doesn't know this notation? EP theta, okay, is less than or equal to, okay, so the EP theta, by definition, this is equal to exponential 2 pi I theta by P. Okay. All right. So, okay. So now, so therefore, okay. So that is less than or equal to cardinality H by P. Now you see, EP theta is always less than or equal to 1, and you are summing over how many terms? H many sums. So this is absolutely a trivial estimate. So far, I have not written, so okay, this is a trivial estimate, and what I am saying is that I can make a saving of P to the power minus delta. All right. So that is the result. So entire the thing is about obtaining this estimate, where you obtain a slight saving over a trivial estimate. Okay. P is sufficiently large. Not for every brand. Okay. Example of what? I am not going to give you the explicit value of this P0. Okay. I will say that P is sufficiently large. How large? I am not telling you. Okay. I am not telling you also what is this delta. Okay. Moreover, actually this method will give you a very bad values of delta. So getting the good values of theta, delta is an open question. Okay. When cardinality of H is greater than P to the power 1/4, then there is another method called Stepanov's method, and that will give you a better values of delta. But the drawback of that method is that it will not work for when the cardinality of H is smaller than p to the power 1/4. This method will work for cardinality of H is greater than p to the power epsilon, but it will give you a very bad values of delta. Alright, so as I mentioned already that when cardinality of H is greater than p to the power 1/4 plus epsilon, then Stephanov's method gives you better results, which we are not discussing. Okay? And when cardinality of H is greater than p to the power half plus epsilon, this is easy to show. Which again in this lecture I am not showing, but I have sent two of you slides of Balu's talk from long back, and that thing contains a proof of, in particular contains a proof of this particular result when H, cardinality of H is greater than p to the power half plus epsilon. Okay? But I will not spend time during this talk in explaining that, though it is easy. Alright, so one corollary for an instance, using this, one can show that, so with the assumptions as is here, sorry. Sorry, thank you. Maximum over xi belongs to Z mod p Z star. There is 1/p both sides. That's how you define generally the average. You can define without 1/p, then the Plancherel and all that, the formulas will, it's a matter of a choice where you put 1/p and where you don't put 1/p. Right. So, okay. So, I am coming to this. This is an additive corrector. This EP H xi. So, xi. So, H going to EP H xi. This is an additive corrector from G2. So from I had defined, which I have removed now, right now, but I had defined. I removed quickly because I thought most of the people will know this notation. Okay? So this is an additive corrector. So what does it says is that the Fourier transform of a multiplicative subgroup under a non-trivial additive corrector. So this xi belongs to Z mod p Z star amounts to that this is a non-trivial additive corrector. EPH xi. So the Fourier transform of a multiplicative subgroup under a non-trivial additive corrector is small. So on one hand you have a multiplication, on the other hand you have addition. and you are mixing both of them. Yeah. No, that is, I mean, so I am not giving you a value of delta. So what do you mean by when does the equality hold? Yeah, so for, okay, so for xi is equal to 0, this is clear that this is mod h by p. So there is no way I can remove this xi belongs to Z mod pz star. Because for the trivial character you have mod h by p and you, that's it. You can't do anything better. Okay? Alright, so statement is clear. Any doubt about the statement? Okay? So the corollary, for instance, with the assumptions as in the theorem, there exists S which depends only on epsilon, a natural number, such that S of h is equal to Z mod pz. Okay? There exists S such that depending only on epsilon, such that S of h is equal to Z mod pz. All right. In contrast, if you know, so if you try to use for instance, many of you might have heard of this Cauchy-Davenport theorem, which basically says that if A is a subset of Z mod pz, then cardinality of SA is greater than equal to minimum of P okay. So rather that's why I was saying that it is better that I remove this font acha. So cardinality of SA is bigger than equal to minimum of P, S times cardinality A minus S plus 1. So if for some S sufficiently large, this thing will start dominating than P, okay, which means that S of A will become the entire group Z mod pz. So you are asking what is the meaning of SA or? Yeah. Such that S of H is equal to Z mod pz. So what it is saying is that which happens in this topic very often. So what is a multiplicative subgroup? In particular, multiplicative subgroup says that if you multiply H into H, it does not grow. It remains H. So any such things which does not grow under multiplication must grow under addition. Okay? Because Z mod pz has no subfields, no non-trivial subfields, and in fact that is at the heart of this proof of this Bruggen-Gilibich-Konya also. It works for Z mod pz because there are no subfields. Because H is a multiplicative subgroup, it cannot be a additive subgroup also. So indeed what it is saying is that when you try to add H, then it will grow very fast. Okay. So then if you try to use what is the value of S for which this thing will dominate, then that will dominate. So S cardinal T A, S of cardinal T A minus 1 should be greater than P minus 1. Cardinal T of A for us is P to the power epsilon. So therefore the S will come to the P to the power 1 minus epsilon along. No, it means S of H is equal to H plus blah 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 plus H S times. Okay? Is it okay? Do I need to define what is S of this H plus H? Okay? So, if you try to use this, then the value of S you will get from Cauchy-Davenport will be around P to the power 1 minus epsilon. Whereas if you use Bürgen-Gliwic-Konyakin, you will get that S is some number which depends only on the epsilon and is independent of the prime P. Okay? And is independent of the prime P. So it gives you much better result in compared to the what the result will be implied by Cauchy-Davenport. What I am saying is that this SA will be Z mod Pz when this is bigger than P. If this thing is bigger than P, then this means that SA, the cardinality of SA is equal to P, because it is minimum. So therefore that will give you S is approximately of the index of the set, means P minus 1 by the cardinality of A minus 1. So that will, in our case, it will give you around P to the power 1 minus epsilon, because the subgroup has the size P to the power epsilon. So it will give you S to be P to the power 1 minus epsilon. All right. So I will quickly review the proof of or indicate to you how the such a result is obtained using this particular result. Okay. One reason is that although it is very elementary, but this kind of things, this kind of ideas are used not just in for an instance in this particular theorem, but it is used in many other situations. Okay, the Fourier transforms comes on to our rescue in many other situations. For an instance, if the A is a subset of Z mod Pz with the certain density, and you want to show that A plus A plus A, 3 times A, contains a arithmetic progression of large length, then you can use this particular ideas. Although not for A subset of Z mod Pz. Zamiridis theorem you can't prove just using this idea, but a weaker version of Zamiridis theorem you can prove it. Okay? Of course, I am hiding many things under the carpet, certain things under the carpet, because Zamiridis theorem is about subsets of integers, and I am telling you subsets about Z mod Pz. But those things are not particularly difficult, but the time consuming. So, section, this is, okay, section 1, I will try to increase the font. Quick review of Fourier transform and convolution. Okay. Again, all these things, this Balu's lecture note slides, which I have sent to Deep and her. So, then that contains all the details, starting from nothing. Oh, yeah. Yeah. So G is a finite commutative group. Okay. For us, G will be Z mod Pz. And for any finite commutative groups, whatever the properties I am going to write to you, even if you don't know, just sit down and do it for yourself, and there is no difficulty in proving any of these things. They are all essentially trivialities. Okay? There are no convergence issues because G is a finite commutative group. You can interchange the sums left and right. And so yeah, so G, yeah. G is, so here for instance, when I am writing G is Z mod Pz, it's a group under addition only. It is not a group under multiplication. If I want a group under multiplication, I have to get rid of 0. Then only it will be a group under multiplication. So entire Z mod Pz is not a group under multiplication. It's a group under addition only. So G hat is equal to chi from G to S1. Chi is so I suppose everybody, again S1, everybody knows the notation. Unit circle. Okay. Chi is G is a group. S1 is also a group under multiplication, and chi is a homomorphism. Okay. So the easy facts. G is isomorphic to its dual in this particular case. It does not happen always, but for the finite commutative groups, it is true that it is self-dual. All right. Moreover, when G is equal to Z mod Pz, given chi belongs to G hat, there exists Xi belongs to Z mod Pz such that chi of G is equal to EP Xi G for all G belongs to G. Okay. So any additive character looks like this. Okay. Maybe I'll remove this. So given a function f from G to C, okay, C for the entire complex plane, and chi belongs to G hat, we define f at chi by definition is 1 by mod G summation G belongs to G Fg chi. In some sense, I would have preferred that if I would have written chi bar here, because then it would have been an inner product. But I saw that in the lecture notes of Balu, and he defined it as to be 1 by mod G summation chi G. So I am being consistent with that notation. Okay. All right. So note that when chi is equal to the trivial character, which we denote by 1, okay, chi is a trivial character. What is f at chi? F at chi, so this becomes just 1, so it becomes an average of f. So it is a mean value of f. So f at 1 is a mean value of f. Okay. So then you have a Fourier inversion, which says that f of G is equal to summation chi f at chi of minus G. Okay, f at chi of minus G. So now I can take out the contribution from the trivial character on one side and write down the other things separately. What happens is that many times the trivial character will give you a main contributions and the non-trivial character will go to the error. Okay? Not always. So therefore, when I write down the contribution from the trivial character, that is, I get m of f, the mean value of f, plus summation chi not equal to 1, f at chi minus of G, which this particular thing I rewrite as EFG, which okay, EFG. Okay. So in many situations, and we will illustrate by examples soon, in many situations, we are interested in understanding support of f, that is, which is by definition is equal to those g for which f of g is not equal to 0. Okay. All right. So now this particular thing says that if mod E of g is strictly less than m of f, then f of g is not 0. So g belongs to the support of f. Okay. So many statements, for instance, the statement which I will do it right now, that can be rewritten. For instance, we wanted to write this S of h is equal to z mod pz for a suitable S, with h being a multiplicative subgroup. So we wanted to say that S of h is equal to z mod pz. So okay, so we will write down the suitable function so that it will essentially amount to saying that everything is in the support of that function. Okay? Everything is in the support of that function. And that function will be nothing but the convolution, S-fold convolution, which I will define. Okay? But in other situations, it will be something you won't be able to do it. That in other situations, you would like to show, in many times you want to show that a support contains certain good structure. For instance, the weaker version of Zamiridis theorem, which I mentioned, that A plus A contains a large arithmetic progressions, you would want that support of A convolution A contains an arithmetic progression. Okay? Then you will understand that what are the values of G for which this inequality holds, and try to show that that particular set contains an arithmetic progression. So rather than showing A plus A contains an arithmetic progression, define a suitable function f and show that the support of that particular function contains a long arithmetic progression, and then deduce that A contains A plus A contains. But the basic thing is just this simple business. Okay. So convolution, so given f1, f2 from G to C, we define f1 convolved with f2 of G is equal to 1 by mod G summation y belongs to G, f1 of G minus y, f2 of y. Okay. So now these are the easy facts, that f1 convolution f2 is equal to F2 convolution F1. Convolution is multiplicative. Okay. And F1 convolution F2 convolution F3 is equal to F1 convolution F2 convolution F3. Okay. So these are all easy things. And another very important fact is the Fourier transform of the convolution is the product of the Fourier transform. Okay. So F1 Fs this is equal to F1 Fs. Why am I talking about convolution at all? So now, although I have defined it for the arbitrary things, suppose this actually lands inside R plus. So F1 and F2 are non-negative real valued functions. Okay. Then again it is not it is quite easy to show that support of F1 convolution F2 is exactly equal to support of F1 plus support of F2. So if I write indicator function of my set A, okay, which is defined from G to 0, 1 as follows, that indicator function of A, x is equal to 1 if x belongs to A and 0 if x does not belong to A. Okay. And by an abuse of notation, I will denote this function to be rather than indicator function A only. Okay. Because we are lazy to write I. Okay. Then in particular, this indicator function is a non-negative function. Okay. So therefore, support of A convolution A is support of A plus support of A. Okay. Here A is an indicator function. But what is the support of indicator function of the set? It is A itself. Okay. So therefore, x belongs to A plus A if and only if x belongs to support of A convolution. And this you can generalize to support of, for instance, A convolution, blah blah blah, convolution A, S is same as S of A. Okay. So S of A, this means S of corollary that S of A is equal to G if and only if this A convolution A S fold x is not equal to 0 for all x belongs to 0. Okay. And using this Fourier inversion, you can rewrite now this A convolution blah blah blah, A convolution X is equal to the contribution coming from the trivial character. That will be the Fourier transform of this convolution at the trivial character. But the Fourier transform of the convolution is same as the product of the Fourier transform. So it will be, so therefore that will be equal to m of A to the power s plus summation chi not equal to 1 A hat chi to the power s chi of minus g. And this is equal to cardinal T A by cardinal T G to the power s plus blah. Okay, but plus this error. Okay. Now, if you have s greater than equal to 3, then and you have an estimate for A hat chi for non-trivial chi, which is what Bourbon-Glibichuk-Koniagin exponential sum estimate is giving you. You can use that to estimate this quantity independent of G by taking out the one thing out or s minus 2 many terms out for the things, and then use Plancherel to to deduce that S of A, that this particular quantity is indeed less than the main term. So therefore, A convolution AS is not zero. All right. All right. So what I am saying is the Fourier transform and the properties of its the Fourier transform with respect to convolution along with the inversion formula tells you that the S-fold convolution of A x is equal to the main term, which is, you know what it is, plus an error which involves A hat chi over the non-trivial characters. And since if you know how to bound that, you can show that EAG, you can hope to deduce EAG is small, provided of course S is sufficiently large. Then only these things will work. And use that to deduce that the A convolution, S-fold A convolution A is not zero at any point, which is equivalent of saying that S of A is equal to Z mod Pz. So you apply that Bourbon-Glibichuk-Koniagin with G is equal to Z mod Pz, A is equal to H, your multiplicative subgroup, and then when S is sufficiently large, depending on the epsilon, this quantity will be smaller than this quantity. So therefore, the term will not be vanished. All right. So now there is enough of the motivation or corollary. Let us go to the come back to the statement of Bourbon-Glibichuk-Koniagin and how we are going to, what is the rough idea of the proof of it. Okay. Now I will, in the next things, when I will tell you the statements, some of those statements are false. Okay. I will tell you what is false later on. Some of the statements will be correct, some of the statements will be false. reason why I do that, because I mean that is how you oversimplify. Because the correct and the complete proof, there is no way I can do in the next 15-20 minutes. The each ingredient will take me more than a lecture. For Feynman sum product theorem, for which the lecture notes are available on the workshop organized in HRI last year, there were 4 lectures of 1.5 hours durations each, and that is just one ingredient. So therefore there is no way I can tell you, give you a proof of it. But I can convince you that these things are related by doing this oversimplification. All right, so let us come back to what is Bürgen-Glebichuk-Koniagin. So you have epsilon greater than 0. H is subset of Z mod PZ star, multiplicative group. Okay, and you want to show, and cardinality of H is greater than P to the power epsilon. Then you want to show that maximum over xi belongs to Z mod PZ star. Hx xi. So what is it? Now, by now we should be that 1 by cardinal 1 by P summation H belongs to H EP H xi. Okay, that is less than equal to cardinality H by P to the power minus delta. This is what we want to prove, and delta should depend only on the epsilon and not on the P. So how are we going to prove it? We will prove it by contradiction. So let delta greater than 0 be such that there exists xi belongs to Z mod PZ star with P to the power minus delta. Okay. What we will show is, we show that if delta is sufficiently small, and that sufficiently small depends only on epsilon, and P is sufficiently large, then we have a contradiction. So I start with the delta greater than 0, for which the inequality does not hold, and I am telling you that if the delta is sufficiently small, then we will obtain a contradiction. And that sufficiently small will depend only on the epsilon and not on the P. Okay? First thing to observe, first thing to observe is that H hat xi is same as h hat h1 xi for all h1 belongs to h. Okay? Here I will use that it is a subgroup. Why? Because what is the right hand side? The right hand side is equal to 1 by p summation h belongs to h ep h1 xi. Okay? So you make the change of variable h into h1 is equal to h prime. Okay? So h is equal to h prime h1 inverse. Right? So therefore this becomes 1 by p summation h prime belongs to h into h1. Okay? EP h prime xi. But h, because since h1 is in h into h1 is h1. So I can get rid of this. So which is the left hand side. This shows that if I have a 1 xi belongs to z mod pz star for which this inequality holds, is violated, what I want, then in fact I have mod h many xi's for which this inequality is violated. Alright? So I have many, I have not just one particular thing, xi for which the inequality is violated, but I have many. This thing is violated. Now if you are careful, then indeed it is not really saying too much, because the cardinality of h is really not that big, because it is only p to the power epsilon. And here I am putting many things under the carpet. Okay? But nevertheless, the philosophy holds. So therefore, but if I have many xi's for which mod h xi is large, that means that this fourth moment is large. Alright? If I have many xi for which hx xi is large, then I have this fourth moment which is large. But if you compute this fourth moment, this is nothing but 1 by p cube into E of h. So let me define. For arbitrary subsets A and B of G, we define EAB. So this is nothing but you just write. I will not prove this thing. I will just define it. But the proof is not difficult. It is just the interchange of summations and using the orthogonalities of the corrector. Okay. EAB is equal to okay. This is called additive energy. Okay. This is called additive energy. So if I have one non-trivial character for which the hx xi is large, what it is telling me is that the additive energy of h comma h is large. So 1 by p cube EHH is large, whatever that large may be. Okay? As I am telling you, I am putting things under the carpet. The real life is more difficult. Okay? Now, Belloc-Zemire-Gauss will tell me that when E of AB is large, or E of, for instance, E of AA is large, then there exists A prime, which is essentially A. Okay? Again, what do I mean by essentially A is under the carpet. It's a dense subset. Dense will depend upon the density, how much large you have, this additive energy and all that. Such that A prime plus A prime is not much larger than cardinality of A prime. Okay? Okay? So the cardinality of A prime plus A prime, so the small subset. See, what is a subgroup? Subgroup is a set which is closed under inversion. It contains 0 and it is closed under addition. Now, in a finite group, if you are, then you don't have to worry about closed under inversion. If it is closed under addition, it will be automatically closed under inversion also. If you are in a finite group, because G times A is identity for every A. If the exponent of the group is M, then M times any element of the group is identity. So therefore, now how do you generalize this notion to the approximate group? That the group is which is closed under addition, and approximate group is something which is not, which is almost closed under addition. So what do you mean by almost closed under addition? Almost closed under addition means that the cardinality of A prime plus A prime is not much larger than cardinality of A prime. Alright? So therefore, this is okay. So therefore, this will show, if I apply this Belloc-Zemire-Gauss theorem here, so this theorem is called Belloc-Zemire-Gauss theorem. Okay, which is basically a lemma in graph theory. Okay. Yes, after a lot of work of several people, things get simplified. There are so Belloc-Zemire proved a theorem. Then the estimates which they had were pretty bad. Then Gauss simplified it. Then Sudakov, who is a professor in Princeton, he came into the picture. Wanwu came into the picture. They further simplified it. So the present proof is which we have is just an application of averaging argument and pigeonhole principle. Okay, so therefore this will tell me that there is an H prime which is essentially H, such that H prime plus H prime is same as H prime. So H prime is a additive subgroup, approximate additive subgroup, but H prime is also essentially H. So H prime, so cardinality of H prime into H prime is also equal to H prime. So it is approximate subgroup under addition as well as a multiplication. So it's an approximate subgroup under addition as well as a multiplication. Then Bürgen-Kastov some product theorem will tell me that it should be like a subfield of the field I am in. But I am in Z-mod region. There are no non-trivial subfields. There is, apart from Z-mod period, there are no subfields. So therefore, that will be a contradiction. As I say, that the details, this will involve quite a bit of work, so I will stop here. These are some of positive terms, and there are many terms for which this thing is large. There are some of non-negative terms. If the sum of non-negative terms, I know that there are many large contributions from individual terms, then the entire sum cannot be small.
But not the second or third moments? Or
Because the fourth moment relates me to this additive energy.
okay.
So this thing which I have not given you a proof is the main thing which gives me a connection between Fourier transform and the addition. Though this is a trivial thing, you can just verify it yourself, but it is nevertheless very important. It is giving you a connection between the Fourier transform and the addition. Yeah, so that's why I say that I am throwing things under the carpet. Reality, it will not work like that. I am cheating here. Yeah.